Hello, students. Welcome to our next installment of Chemistry Basics and Atomic Structure, our N5 notes, to be followed by N5 KCQ boxes. So we'll jump right in. All right, so John Dalton, way back in 1808, came up with an atomic theory, and his first thought was all matter was composed of extremely small particles that were called atoms. And everyone kind of agreed with it. He was the smart guy of his time in the field. He also said that atoms of a given element are all identical. So if I have all just iron or all just helium, every single atom in the sample has the same size, the same mass, and the same properties. Next, he said that atoms of different elements, so when comparing one element to another, he could confidently say that atoms of different elements had different sizes, different masses, and different properties, which hopefully still makes sense today. Fourth, he concluded through experimentation that atoms cannot be subdivided, created, or destroyed. He couldn't carry out a reaction and make a new element, or carry out a reaction and remove an element. It no longer would cease to be there. Couldn't split atoms, couldn't make them smaller into smaller pieces. Next, he came up with the idea that atoms of different elements will combine in simple whole number ratios to form compounds. So looking at water, H2O. If you look at glucose, C6H6O6. What's the ratio of carbon to hydrogen to oxygen? The simple ratio. No, it should be a 1 to 2 to 1 ratio. If you look at acetic acid, the stuff that's in vinegar, C2H4O2. The simple ratio of that one is also a 1 to 2 to 1 ratio. So glucose and acetic acid have the same elements involved, but because they are at the same ratio, but a different number of atoms in their compounds, they're completely different. Acetic acid and glucose, very different molecules, yet they have the same whole number simple ratio between the elements in that compound. And lastly, he realized in chemical reactions, atoms do combine, or they come apart, or they are rearranged to make new things, but everything stays. Like earlier, we're not saying we lose any elements or gain any elements. The ratio of elements to start with has to be the same beginning and the end. Law of conservation of mass hasn't changed. Unfortunately, modern atomic theory has come up with a couple things that actually have proven Dalton's theory incorrect. All atoms have an average mass. Now, this is an average mass because of the existence of isotopes. So, take hydrogen, for example. Hydrogen has three isotopes, H1, H2, H3, each having the same single proton, but they do differ in the number of neutrons. Deuterium, which is H2, is what they usually call heavy water. So it's still H2O, but all the hydrogens are made with the isotope deuterium instead of just regular hydrogen. Tritium, if you ever saw one of the original Spider-Man movies with Dr. Octopus, in that movie they used tritium to make a sun, if you will, perpetual energy. Pretty cool movie. It's old, but so am I. The other thing that they proved Dalton's theory incorrect was due to the fact of nuclear reactions. Atoms cannot be divided, created, or destroyed under normal chemical reactions. So according to Dalton, he was correct in that fact. But at the time, nuclear reactions were not discovered, they weren't known about. But through fission and fusion, atoms can be cut in half. Fission, atoms can be pushed together and combined. Fusion, in order to make new elements, similar to like the CERN super collider in Geneva, Switzerland, that is talked a lot about in the Big Bang Theory. If you guys ever watch that show, they're throwing atoms at each other at high velocities near the speed of light to try and create something new. So Dalton, at his time, was correct, but obviously with modern theory, he has been proven wrong in these two very important aspects. So later on, the discovery of the electron occurred by J.J. Thomson, and he used a cathode ray tube to deduce the presence of a negatively charged particle. And we are going to go to that video if I can find it. Not there. Hold that thought. This is awesome. There we go.
Writing's not that easy, but Grammarly can help.
Skip this thing.
This sentence is grammatically correct.
Okay, this is a cathode ray tube. What it essentially is, it's a vacuum chamber. There are no gases inside this glass tube. The only thing we have are two electrodes, one's called the cathode, the other's called the anode, and a fluorescent screen in the background. It's close.
Oh, hold that thought, because clearly it wasn't working, so I'll just go to the link now and show you guys. So let's come back. So by now we have seen the video of the cathode ray tube showing us what's going on with it and how it proved the existence of some negatively charged particle. So you'll have access to this video clip as well. It'll be in the PDF, hopefully, version of the notes that you can click on. All right, so conclusion from the study of the electron. Cathode rays have identical properties regardless of the element used. So it didn't matter, the same result occurred every single time. Therefore, all elements must contain this negatively charged particle that we call electrons. We do know that atoms are neutral. So clearly there has to be some positive particles balancing out the negative ones that are electrons in order to keep an atom neutral. We also figured out that electrons are very little in mass compared to the rest of the atom. So atoms must contain some other heavier particle that can account for this mass. A little late on the arrows, but okay. So Thomson's model, when he took all his information, all his data, he came up with this plum pudding model. And his idea was the plums were embedded in this positively charged pudding that supported what he was trying to say and what he was trying to get across to the scientific community. The electrons are not moving. Plums don't really move around plum pudding. So they were able to come up with, or he was able to come up with, this idea. There was a positive thing, and then there was a negative particle as well. Another example of it. So later on, Rutherford, Ernest Rutherford, who was Thomson's student, came up with a gold foil experiment. As you can see from the diagram, there's an alpha emitter. An alpha particle is basically a helium nucleus and stripped of all electrons, so it's just positive, and he fires those things at a thin piece of gold foil. And then the particles go through and hit a detecting screen that are all around it, the blue screen that you see. But interestingly enough, the the alpha particles didn't all just go straight through. Majority of them did, but some of them were deflected. And you can see by this image on the right-hand side that some kind of ricocheted off, or they bounced off and came back. Some even came straight back to the alpha emitter. So what was going on? Something happening here that was unknown and not sure and wasn't even expected. So let's go over to our video. Okay, we've watched our video and now we are back. All right, so Thomson's model gave the idea that electrons were there. They were very, very small and then surrounded by this pudding. But according to Rutherford, something else was going on because the alpha particles were not just going straight through. Something else had to be there. So his findings, again, most particles went straight through, and that's what they assumed everything would do. All particles should go straight through, no movement. But some were deflected, and that was seen on the detector screen. But some of them, or few, were actually greatly deflected. Sorry, I can't talk. Which gave rise to other ideas and more data pointing to something else is going on. Here's Rutherford. So ultimately he concluded there's got to be a nucleus and it's got to be small, because if most of the particles went straight through, then the nucleus does not take up that much space. The nucleus has to be dense. If alpha particles, which are themselves helium nuclei, then for two objects to bounce off of each other or deflect one another, it's got to be dense, it's got to be hard. And then lastly, he concluded that the nucleus, it's got to be positively charged, because any of the particles that got near the nucleus were deflected, not by hitting each other, but what happens when you get two positives near each other? They're going to repel. So because of the fact that some did repel versus some bouncing, and you can tell that by the angle at which things change versus going straight through at 180 degrees, this conclusion can be made that the nucleus has to be positive. And then the atom is mostly empty space, which is backed up by Thomson's idea that most of the particles went straight through. Very few were actually deflected. So the nucleus has to be small and the atom is basically empty space. Yes, there's electrons there, but they're so small compared to the size of the nucleus. That's why we come up with this idea that it's mostly empty space. So Rutherford took Thomson's model and stuck positive particle right smack dab in the center. Electrons are surrounding it. Still, they're not moving. We're not showing any movement here, but they are placed around that center nucleus idea. Along came Bohr. Niels Bohr was Rutherford's student. So yes, they're all each other's students and then become teachers. Bohr came up with the idea that electrons, they're actually moving. And his idea was the planetary model, where the electrons orbit the nucleus following these circular paths. Today, definitely not true. But at the time, it gave, through his experimentation and his looking at data and thinking about what's going on, he came to this conclusion that the electrons are moving. But today, we have this idea of the quantum model. Electrons are basically bees around a beehive, especially if you play with the beehive, the bees go crazy. So Now the quantum model suggests these orbital things, which we're going to get into later, much different than the other previous models, but due to quantum mechanics and learning more information, it brings rise to this as our kind of standard today of what an atom looks like based on how it's built. So our particles, these should be familiar with you guys. Electron, proton, and neutron, their charges, their mass, and their location. You guys should have learned this back 7th and or 8th grade. We give the electron a mass of 0. Does it actually have a mass? Of course it does, but it's on the order of 10 to the minus 27 kilograms. Extremely small compared to a proton or a neutron. So that's why we give it a arbitrarily, that's not the right word, I'm sorry, but a mass of 0. All right, so our atomic number of protons in the nucleus of each atom in the element, pretty straightforward. So you look at a periodic table, carbon has 6 protons, so it has an atomic number of 6. The atomic number is symbolized by capital Z. Why? I have no idea. It's just what they went with. So again, number of protons is always equal to the atomic number, right on the periodic table. Easy to find, easy to use. Now, the mass number is the number of protons and neutrons added up together in the nucleus of the isotope of that atom or element you are looking at. So mass number is pretty easy. Proton plus neutron. The mass number is always a whole number. So keep that in mind. A mass number is always a whole number, not a decimal number. So this little chart for a second. We'll fill it out kind of together. You don't need to write it down. It might be in the gluons. I don't remember at the moment, but I will hit pause and let you know if I remember. But again, pretty straightforward. Oxygen on the periodic table has 8 protons. Therefore, it has to have 8 electrons to be a neutral atom. Mass number is 18. Just add proton plus neutron. Pretty easy, pretty straightforward. And then the symbol, if you will, is oxygen-18. Look at the next line, 33 protons. Periodic table says it's arsenic. It's neutral, so it's got to be 33 electrons. Mass number, again, add up 33 plus 42. Again, basic math, easy stuff to do. Symbol, arsenic 75. Third line, number of protons is 15. So we can look at the periodic table and figure out what element that is. In the left-hand column, it says 31. That's my mass number. So if I know my number of protons and I know my mass number, you should be able to figure out what the number of neutrons is. We know it's phosphorus from the periodic table. We know it's neutral because equal number of electrons and protons. Therefore, my neutrons, through subtraction, is just 16. Any questions on filling out this chart? All right, take a moment, read the question, and mentally think of your answer, or write it down off the side of your paper. All right, number of protons should have been what you had, or what you chose. A number of protons, the atomic number, as we said, is the identity of the atom. So keep that in mind. Only protons can identify the atom because every single element, has a different number of protons. All right, ions. Ions, when you change the number of electrons in an atom. So we're keeping the protons the same, we're just changing the number of electrons. 2 different names, cation right here, anion right there. Cation, loss of electrons, so you end up having more protons to electrons. You got to be a positive charge. One example, calcium 2+, versus an anion where you gain electrons. So the number of protons versus the number of electrons is less, Therefore, it's a negative charge. For example, nitrogen with a 3- charge. Isotopes, what we brought up earlier as one of the issues with John Dalton. Atoms of the same element having a different mass due to varying number of neutrons, as we brought up earlier. I brought up the example of hydrogen. So protium is just your basic hydrogen, deuterium, as I said, and tritium. You can see they all have the same number of protons. So hydrogen has to have 1 proton. That can't change. But notice the number of neutrons is different. That's what gives rise to them being isotopes. So a couple images just to kind of see what's going on inside the nucleus. All right, so average atomic mass is much different than the average you're probably thinking of. Ultimately, we look at the average of all the naturally occurring isotopes of that element. So if we take carbon-12, we're all familiar with carbon-12, that's living things. Carbon-13 and carbon-14 are actually radioactive. Use them for radiocarbon dating, see how old dinosaur bones are, for example. Now, interestingly enough, majority of the carbon that exists is carbon-12. There's very, very little carbon-13 and even a smaller amount of carbon-14. But the overall average atomic mass of carbon is 12.011. In your guys' idea of average, you would have taken 12 plus 13 plus 14 and divided by 3, which would give you 13 as your number. However, that assumes, for the moment, that there's equal amounts of all 3 types of carbon. We can clearly see on the right-hand column, they do not all equal the same amount present in nature. So that's why we cannot add up the total and divide by the number of things. It doesn't work that way with elements because they're not equal in their abundance. Go back a second. So on our next presentation, we'll look at how to actually calculate this more in depth. Thank you very much. Have a good rest of your day.